This time, we will look for the vector valued function of the curves of intersection of the given pairs of surfaces. To start with, we have the pair z equals 9x squared plus y squared and y equals x squared. As noted from the lecture, it is not necessary to graph the surfaces, but to satisfy our curiosities, let us look at the graph first. So here we have the graph of the two surfaces, the elliptic paraboloid z equals 9x squared plus y squared together with the surface regenerating curve y equals x squared, whose rulings are parallel to the z-axis. From here we see that the curve of intersection is a parabola. Now going back, note that both equations contain the variable x. Moreover, our second equation is written in terms of x. Thus, if we let x to be our parameter t, from the second equation, we obtain y equals t squared. And from the first equation, we can solve for z to be equal to 9t squared plus t squared squared, which is t to the fourth. And thus, we obtain the parametric equations of the curve of intersection given by r of t, which is equal to t squared, and 9t squared plus t to the fourth. This time, we want the parametric equations of the curve of intersection of this unit sphere x squared plus y squared plus z squared equals 1 and the plane z equals 1/2. Before that, here's the illustration of the curve of intersection, including the graph of these two surfaces. As mentioned before, here is the graph of a unit circle and the plane z equals 1/2. The curve of intersection is a circle. Unlike the first example, in here we don't need to define any of the variables as the parameter t. Note that since the two equations are simultaneously satisfied and z is a constant, then we can plug it into the first equation, which yields x squared plus y squared plus 1/2 squared equals 1. Simplifying, we have x squared plus y squared plus 1/4 equals 1, giving us the equation x squared plus y squared equals 3/4, which again, we are familiar with the parametrizations of. This time, we let x to be square root of 3 over 2 cosine t, since this is a circle of radius square root of 3 over 2. And y equals square root of 3 over 2 sine t. Then, the vector valued function is defined as r of t equals square root of 3 over 2 cosine t, square root of 3 over 2 sine t, and 1/2. Moving on to our next pair of surfaces, we have the circular cylinder 9x squared plus 4y squared equals 36, and the plane 2x minus 3y plus z equals 1. Again, here is the illustration of the curve of intersection of this pair of surfaces. This time we have the graph of a circular cylinder 9x squared plus 4y squared equals 36. And the plane 2x minus 3y plus z equals what? Here's how the curve of intersection looks like. For this example, we don't have the convenience of having one of the surfaces to be defined as a constant variable. Moreover, letting any of the variables to be equal to our parameter t might not be helpful. Luckily, the first equation here we can rewrite as x squared over 4 plus y squared over 9, which is equal to 1. Again, from our previous lessons, we are familiar with the parametrizations of these types of equations, which are ellipses in R2. We can let x to be 2 cosine t and y to be equal to 3 sine t. And from the second equation, we can plug in these two parametrizations in order to solve for the variable z. So we have 2 times 2 cosine t minus 3 times 3 sine t plus z is equal to 1, which simplifies into z equals 1 minus 4 cosine t plus 9 sine t. Hence, the vector function of the curve of intersection of this pair of surfaces is given by r of t, which is equal to 2 cosine t, 3 sine t, and 1 minus 4 cosine t plus 9 sine t. And that is the answer. Lastly, let us consider the pair of surfaces z equals x squared plus y squared and 4 equals 3x squared plus y squared plus z. These two are elliptic paraboloids, as we can see in the illustration. Lastly, we have the graph of these two elliptic paraboloids. The graph of z equals x squared plus y squared is the red one, while the graph of 4 equals 3x squared plus y squared plus z is the blue one. The curve of intersection is over there. And we're back again. For this example, note that the second equation can be written as z equals 4 minus 3x squared minus y squared. Thus, we obtain two equations which are both equal to z. Equating the two equations, we have x squared plus y squared equal to 4 minus 3x squared minus y squared, which simplifies into 4x squared plus 2y squared equal to 4. Dividing both sides by 4, we obtain x squared plus y squared over 2 equal to 1. So we can let x equal to cosine t and y to be equal to square root of 2 sine t, which is the parametrization of the said equation. Now, solving for z, we can choose any of the two equations. I will choose this one so that we have z equal to, substitute x, cosine squared t, substitute y, plus 2 sine squared t, which gives us the vector valued function r of t with components cosine t, square root of 2 sine t, and cosine squared t plus 2 sine squared t. And that is the answer. Now, the last few exercises we will be doing are quite straightforward since we will only be familiarizing ourselves with operations on vector valued functions. For the rest of the discussion, we will be using the two vector valued functions denoted as capital F and capital G, defined as follows, and the two real valued functions denoted small f and small g, defined as follows. So first, let us try to compute for the dot product of our two vector valued functions f and g. So we will be computing for f dot g of t. Again, this is quite straightforward. The dot product of f and g is simply the sum of the component-wise product of f and g. So we will be taking the dot product of 4 minus t squared, 4, negative 4 minus t squared, and t squared minus 4, negative 4. Thus, we have 4 minus t squared times t squared plus 4 times t squared minus 4 minus 4 minus t squared times negative 4. Expanding this, we obtain 4t squared minus t to the fourth plus 4t squared minus 16 plus 16 minus 4t squared. Thus, we can cancel 4t squared with minus 4t squared, minus 16 with plus 16, which leaves us with 4t squared minus t to the fourth. And this is the answer. Now, what if we want to look for the cross product of capital F with capital G evaluated at 1? From the definition of the cross product of vector valued functions, we know that this is just capital F evaluated at 1 cross capital G evaluated at 1. Thus, we can first evaluate f at 1, which gives us the vector 4 minus 1, which is 3, 4, negative quantity 4 minus 1, which is negative 3, cross with the vector function g evaluated at 1, which gives us the vector 1, 1 minus 4, which is negative 3, and negative 4. If you remember the formula for the cross product, then you may proceed with the computation of the cross product of the two vectors. However, if you don't remember it, it doesn't hurt to set up the determinant matrix of the cross product. So we want the I hat, j hat, and k hat components 3, 4, negative 3, and 1 minus 3, negative 4. Now solving for the I hat component, we have 4 times negative 4, which is negative 16, minus negative 3 times negative 3, which is minus 9, I hat. Then minus the j hat component, which is obtained by multiplying 3 times negative 4, which is negative 12, minus 1 times negative 3, which is positive 3, j hat. And lastly, for the k hat component, we can obtain it by multiplying 3 times negative 3, which is negative 9, plus, minus 1 times 4, which is minus 4, k hat. Simplifying this, we have negative 25 I hat plus 9 j hat minus 13 k hat. And this is the final answer. This time, let's take the scalar product of small f with capital F. That is, we want f times capital F of t, which is as simple as multiplying the function t, 1 over 2 minus t, with the vector valued function capital F, whose components are 4 minus t squared, 4, and negative quantity 4 minus t squared. We simply distribute f, that is, we multiply f to each component of capital F. Note that 4 minus t squared can be factored out as 2 minus t times 2 plus t. So distributing 1 over 2 minus t will give us 2 plus t, since 2 minus t will be cancelled. 4 over 2 minus t, and negative quantity 2 plus t. And this is the answer. Now for our last exercise, let us compute for the composition of the vector function capital F with the real valued function small g evaluated at negative 2 by the definition of composition of vector valued function with real valued function. This is simply capital F evaluated at g of negative 2. Substituting negative 2 to g of t, we obtain f of 2 minus negative 2, which gives us f of 4. Thus, plugging in t equals 4 to our vector valued function capital F, we obtain 4 minus 16, 4, and negative quantity 4 minus 16, which we can simplify into negative 8, 4, and positive 8. And this is the final answer. And this marks the end of our discussion. I hope we all learned something from this video.